Hi everyone. Thanks for coming for the talk. I'm Daniel.
I'm Nikhil.
And today we're going to talk about TensorFlow.js. Before I go into the next slide, I just want to say that this has been a work of many people. As you can see on that slide, we've been going on for a year and a half, maybe 2 years. And there's a lot more to do. So how many people here are think that they're comfortable doing Python? I'm just curious. Writing Python code. Okay, almost everyone. So this is not a surprise, right? Python is synonymous with scientific computing today and doing numerical computations. And as you can see here from this software poll from KD Nuggets, it's the top data science software. How many people here are comfortable writing JavaScript code? All right, I don't see that many, but still quite a few. I'm very glad. So JavaScript, on the other hand, is extremely popular as a language. And this chart here that is from GitHub shows how many open pull requests there were in JavaScript and other languages in 2018. Another thing about JavaScript is that the community is very diverse, and a lot of people don't come necessarily from scientific computing. In fact, in the early days of TensorFlow.js, the early adopters were people that wanted to do creative coding, that wanted to use ML in a creative way. Another thing about JavaScript is that, runs in a browser, and as you know, in a browser, if you build something, if you write a blog post, you share a link, someone can then is click away from seeing your work. It is also highly interactive. Browsers have all the UI. They also run on laptops and cell phones, mobile phones, and all of these devices have sensors such as microphones and cameras and accelerometers, and they're all exposed behind standardized web APIs. All of these interesting, unique things about JavaScript lead to developers being able to build new class of distinct applications that can take advantage of on-device computation, low latency, and privacy and accessibility as well. I wanted to say a little bit more about the JavaScript environment for those of you that are not very familiar. It's supposed to run anywhere. It has a virtual machine that can execute it, except that it ranges all the way from server-side in Node and client-side in browsers. And the APIs don't overlap as much. They overlap within 50%, but when one builds a library, you gotta aim for the intersection of those. Another thing that's tricky about JavaScript is it's an interpreted language. And that means that performance can be tricky because it can run near the speed of C if you write your code carefully so that just-in-time compilation of V8 can execute it as C. But if your code is part of a transpiler that takes ES6 to ES5 code and that transpiler rearranges the variables, it can hurt your performance by a lot. So you have to be careful when you're writing a JavaScript library to account for these effects or to have a backend where you can offload your computation to something that is much more stable and predictable. Another thing when you target browsers, for instance, like we do, is you have Firefox, you have Safari, you have Chrome, and there are all these there's a W3C standard, and there are all these standards that all browsers should implement, but in practice, they all do things slightly differently, and then you have to account for that too. And I'll just end this slide with saying that JavaScript is single-threaded, which makes it easy if you do many things in parallel and not be blocked by all the multi-threaded problems. But the way that they resolve this is with asynchronous programming, which takes a while to wrap your head around. Just a quick mention of related works where we were not the first to do ML in JavaScript. There are a lot of libraries out there. This chart shows us along other libraries, along axes such as whether they use the GPU, whether they're actively maintained. I just want to call out that as of today, we're the only library that's actively maintained and has a full API to write author graphs and to do training and do backpropagation. A few other works that back in the days when we were developing this early on were maintained, and now they are not. A little bit about our design. So we have performance is very important, and for us, we're going to talk a little bit more about that and how that made our projects basically possible. But when we were conflicted, when there was this struggling force between making it easy to use and performance, we would choose easy to use first because we wanted to, bring ML to a new set of community, and we don't want to, make it extremely hard. At the same time, our library, we wanted to have wide functionality because we wanted, experts that know both Python and JavaScript and that can develop these ML models to be able to come to our platform and then share their work. And we wanted those experts to have access to gradients, to all the ops, to be able to, let's say, build educational content if you're an educator, and so forth. And these two goals of being very easy to use and also have wide functionality are in conflict often. And the way we kind of resolve that is to have multiple layers of abstraction. And what I mean by that is that at the API level, we have 3 layers. So we have the core API where you can write ops like matmul and add and multiply. And they all run in eager mode, just like TensorFlow 2.0. On top of that, we have the layers API, which is modeled after Keras. So you have high-level building blocks such as layers, convolutional. And on top of that, we also have a repository of pre-trained models. So you can use them off the shelf without even knowing about tensors and about multidimensional arrays, where the output can be just a JSON object. On the backend side, so all of this API bind in the browser utilizes WebGL to actually utilize the GPU and that gives us a significant boost. On the server side in Node, we can bind to anything, so we bind to TensorFlow C, which then can utilize GPU, CPU, TPUs. And lastly, if you have an existing model in Keras or TensorFlow saved model, we have converter tools that can allow you to automatically port your model to the web or server side. And just to give you a little bit of a code example, so we tried to make it extremely easy to use, very JavaScript-like. Unfortunately, the only thing that we couldn't account for in the browser was texture garbage collection of WebGL textures, which browsers don't collect. And for that, we have a tidy construct. And this example here shows that. So if we have here a function on animation, which gets called, let's say, 60 frames per second, and we run the image through our model function, and then we display our result. And here we have to wrap it in a tidy, and tidy is just a scope that we introduce, so it can monitor all the tensors inside, and then dispose everything but the result. So that's why Y is the only thing that we need to dispose. So this is for experts. The way to kind of hide that is you can use our high-level API layers model and then call model.predict, and you don't have to do a tidy. The only thing you have to take care of is the output, Y. And even further than that, if you're using one of our off-the-shelf pre-trained models, you pass in an image, you get a JSON object back, and you don't have to take care of any memory management. All right, so a little bit about performance. So the top right chart here compares TensorFlow.js on various backends. One thing to take away from this is that WebGL is what made this project possible to do ML in the browser, because it is 2 orders of magnitude faster than plain JS. And we are actually actively working on making WebGL faster. We have recently added packing. This is after we wrote the paper, which allows us to store values more efficiently in texels, and that can lead to anywhere between 1.4x to 9x speed up on some devices. Another thing I'd like to point out is that there is still a 3 to 10x cap between WebGL and CUDA for large batch sizes. For a batch size of 1, we don't see that. And here, we suspect it's because WebGL doesn't give us shared memory access or worker pools that CUDA does. But new technologies are coming up, and we believe that WebGPU and compute shaders will narrow this gap. And the chart on the bottom right shows TensorFlow.js binding to TensorFlow C server side and Python binding to TensorFlow C server side. And we see that we're on par with Python for inference because we're just a thin shell. For training, though, we're still working on it because training involves a lot of code that needs to be written in JavaScript itself for gradient, and we're making that faster these days. I'm going to let Nikhil. tell you.
All right, thanks a lot. So in the browser, the way we do this is we use a technology called WebGL. Now, WebGL is a way for the web to bind to OpenGL, which is a way to express graphics constructs that run on your GPU. Now, little known fact in the deep learning world, the G in GPU stands for graphics, not something else like gradients. So what we do is we actually store all our tensor data in WebGL textures. These are 2D textures. And we write all of our programs as fragment shaders. Now, what OpenGL is really good at is drawing pixels on a screen, and they'll do that in a very massively parallel way. So we actually kind of take advantage of that parallelism to do linear algebra constructs. So in this example we're looking at is an element-wise addition of two matrices, A and B, to compute a C. What you're actually seeing in that box is the implementation of that fragment shader. And the fragment shader is a little mini program that's going to run in each of the output cells of C. And OpenGL will massively parallelize that, so we get really nice speedups from that. So to jump into an actual fragment shader, this is the matrix multiplication. This is GLSL code. This little main mini program runs again over the context of all the output cells. These little bolded functions here are not raw GLSL. These are TensorFlow.js provided constructs that we've actually assembled together as the program is about to be executed. Now, we actually opted to write real GLSL code rather than write a little compiler on top of that. We did that because we wanted to just make it a lot easier for us to debug, and it's been working out really nice. Okay, so that was the browser. On the Node.js side of things, which is a way to run JavaScript server-side, if people don't know about that. We actually bind, again, as Daniel says, to the TensorFlow C++ API. We do that with an API. And JavaScript is really, really a fast language, so we actually can, see similar or even sometimes faster than Python when we do this, which is pretty nice. One of the amazing things about Node.js is we have finalization for things like that we don't in the browser. So WebGL textures, the where we store GPU memory, don't get automatically garbage collected. So we have these tidy constructs, which are kind of unwieldy for JavaScript programmers, let's put it that way. So in Node, we actually have a hook into finalization because we're kind of unconstrained by the browser environment, which is really nice. And we're actually working right now on headless GL binding. So that means in Node.js, being able to run our OpenGL shaders inside of that headless environment. That enables GPU acceleration on devices that we weren't able to before. So this is on like Macs, on Raspberry Pis, and other IoT devices. So that's pretty cool. We're also really interested in performance. So we're thinking about some new backends for TensorFlow.js. On the CPU acceleration side, there's a standard called WebAssembly. This is a way to take C++ or Rust code, compile it to a little binary that runs and is interpreted in the browser and can run close to C speeds. That in combination with SIMD, which is going to land pretty soon in browsers, and that with worker threads, which you can actually use native C++ P threads, and those will actually run multi-threaded code inside of a browser, which is kind of a new thing. That combination, we think, will get us a little bit closer to WebGL speeds than we're getting today. There's also a new GPU standard called WebGPU that's going to land pretty soon. This has already been spec'd out and is now in implementation stage. This is a general purpose GPU programming construct for the web. So think about CUDA for the web. So we're working pretty closely with Chrome on the implementation of that, and we'll hopefully have a prototype later this year. We're also part of this W3C community group to standardize what we're calling WebNN. This is a way to expose neural network concepts directly to JavaScript, maybe like TF, or not TF, something conv2d in the browser. And under the covers, the browser will be binding to the native hardware acceleration depending on what that device is. Maybe on Android it's NN API, or on Macs it's Metal. So we're actively part of that discussion. Okay, so one of the important things that we wanted to do with this project too is have the ability to move between the Python world, which is this massive rich world of models, and the JavaScript world. Otherwise we would be sort of an orphan. So what we did was we built a model converter. This was a way to take a Python model, a TensorFlow saved model, a Keras model, and port that directly to the browser for inference. And we also built a models repo on top of that. This is off-the-shelf NPM packages that you can just go and install, and they require no tensors and no knowledge of linear algebra. You just kind of point to a video tag and you get JSON objects out, and we host all the weights for you. So one of the cool examples of that is this model called PoseNet. I'll show you a link to that at the end. This takes RGB images and it'll give you poses out as a JSON object, which is pretty nice. Just to jump through a couple things here, one of the really interesting things about the JavaScript environment that I think a lot of people don't know is it runs in a lot of different places. So one of them is the browser, but it runs in tons of other environments as well. So I'm going to quickly talk about a couple examples that people have built. One is Creatability. This is an accessibility experiment done by some Googlers to basically take RGB images from webcam and try to basically control the computer with just your face. Uber has used us as a linear algebra library, not even machine learning, just for forward mode linear algebra in this project called Uber Manifold. Airbnb has actually used TensorFlow.js as well to ship a little mini model to the client that says when you're about to upload a profile picture, don't upload a license, don't upload any government issued photos, and they tell you that right on the device before they get it on their servers, which is pretty nice. So on the Node and desktop side of things, in Node.js there's a program called Clinic Doctor. It lets you take a Node.js application using a TensorFlow.js model and differentiate the CPU usage spikes between the actual CPU program that you wrote, your code, and the Node.js kernel itself. And Magenta Studio, it runs in an Electron app. So this is Electron is a way to run JavaScript as a native application on your device. So this is a tool that lets artists go and generate new types of MIDI files, maybe just spark some creative idea before they move on to the next thing. And on mobile, there's a whole rich ecosystem called WeChat in China. So this is an application that has a whole app store inside of that application with 1 billion users, 1 million developers, a ton of things going on in here, and they run entirely in JavaScript. But they look completely native. So we're working to get OpenGL bindings working with TensorFlow.js as well on that platform. So everything we talked about here is open sourced. If you want to waste some time, go check out our demos on tensorflow.org/js. There's lots of fun stuff there. You'll have lots of fun. All the code is open source here as well, and we want to thank all the people who have worked on this project as well. I think we have some time for questions. Thank you.
All right, if we have any questions, please come up to the mics.
Hi there, congratulations on the really good work. I have a question about the API and how different it is from the Python API.
So in general, we try to stay as true to the Python API as possible. So every op that we support has the same list of arguments in the same order. There are a few differences that we have to deal with in the JavaScript ecosystem. Specifically, memory management is one of the major differences. The way we actually interoperate with browser APIs. So if you want to get a tensor from a video tag, we have to invent something because that doesn't exist in Python. So there's a few things that are different, but mostly we try to stay true to that API. And then the layers API that we provide, that high-level API, is pretty much the Keras API.
Thank you. Are there any more questions? All right, with that, let's thank the speakers of this session.